Good day, everyone. In this video, I will aim to provide a brief digest of material on self-supervised learning and pseudo-labelling. This material forms part of some lectures I gave in 2021 as part of the 4F12 lecture series at the University of Cambridge. To provide a brief outline for the video, we will start out with self-supervised learning before moving on to pseudo-labelling. We'll start out with the first topic. Let's begin with the motivation for self-supervised learning, starting with a summary of the state of the nation for the world of machine perception. We have a number of reasons to be cheerful. Deep learning has given us remarkable progress with the supervised learning paradigm, in which we gather a large collection of data and manually annotate it, and supervise a model with the resulting annotated data. This has yielded truly major gains on vision benchmarks. Of course, benchmarks are not the goal in themselves, and they have drawbacks. They can trap you into a local minimum of research ideas, but they have clear value in allowing an objective comparison of different methods. Still, we have some cause for concern, and somehow it seems that we might still have a long way to go. Even the highest capacity models trained on the largest annotated datasets continue to make what we might call silly mistakes that would be never made by a human. Perhaps more worryingly, it seems that we can just never get enough labeled data to get close to the human perception system. This state of affairs prompts a natural, age-old question. Can we take inspiration from the early stages of development of human perception to improve things? To answer this, it's worth considering the wealth of research that has studied human development in some detail. Human baby learning is incremental. A child learns in a continuously evolving environment rather than a stationary distribution. Social. Babies learn from other humans around them, particularly caregivers. Physical. They offload knowledge to the physical world around them and store information with respect to their surroundings. Exploratory. Once their curiosity is aroused, they try a lot of things to try to find something that works. Learning is language-based, allowing them to not only communicate, but also learn abstractions that support generalization. Finally, their learning is highly multimodal, experiencing sensations from sight, sound, touch, taste, proprioception, balance and smell when these senses are available. Different modalities provide significant redundancy among their inputs to learn from. It's also interesting that babies naturally build curricula for their learning. Careful analysis of the appearance of objects observed by babies shows that they follow a strong power law. A small number of objects are seen an incredibly large number of times, such that the child becomes an expert in recognizing and manipulating those objects. Okay, this all sounds great, and many people have observed that our current machine perception systems are doing very little of these human-inspired learning strategies. Why is that? I would say that the main barrier to implementing the kind of embodied perception learning exhibited in babies has been practical. In fact, this challenge was noticed by Alan Turing, who was interested in the development of such machines, and observed in 1948 that in order that the machine should have a chance of finding things out for itself, it should be allowed to roam the countryside, and the danger to the ordinary citizen would be serious. The takeaway here is that there is some practical challenge to embodied learning, which is the general term given to an agent possessing a body that learns to interact with its environment. It's possible that recent developments in simulation may help us here, but we're still some way away from creating the world in sufficient fidelity to have fully addressed this problem. For that reason, we will talk about a family of methods that tries to make progress principally on perhaps the safest of the human learning characteristics, multimodal learning. In particular, we will discuss self-supervised methods that are partly inspired by human multimodal learning in the sense of exploiting redundant signal. The essence of self-supervised learning, as you might infer from the name, is that the learner should create its own supervision. This is an old idea that was nicely articulated by Helmholtz in his legendary 1878 speech on the facts in perception. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial dimensions. So we can create a plentiful supply of learning targets by simply moving and checking whether our model of the world was able to predict what we will see. The role of redundancy in sensory signals was then considered more explicitly by Barlow, who made the observation that learning requires previous knowledge. In particular, to detect a new association, such as the event C preceding event U, we need to know the prior probabilities of C and U. If we have those, then we can learn a new association if we observe that C is followed by U more frequently than would be expected by chance. The key role of redundancy is that in order to know what usually happens, we need redundancy in the input signal, which could be, for example, sensory messages of the same event from different modalities. The redundant signal is, by definition, the part of the signal that can be predicted from the remaining signal. This redundant signal provides labels for training a predictive model. One computational trick that is nicely illustrated in Barlow's work relates to the kinds of codes we can use to represent events in our environment. The observation is the following. To test whether two events are co-occurring more frequently than would happen by chance, we need to know their prior joint probabilities. So when learning pairwise associations between n events, we need to store n squared co-occurrence probabilities. But if we've learned representations in which events C and U are statistically independent, we can compute the chance co-occurrence of C and U from the product of their marginals. That means we only need to store n event probabilities. This can help to avoid a combinatorial explosion of storage for prior event probabilities. Barlow himself suggested minimum entropy coding as a scheme to obtain factorial representations, but this idea applies more generally. It's always desirable to achieve this property where possible. One of the first works to use the term self-supervised that operationalized this insight about learning from redundant signal was proposed by Virginia Dessart in the 1990s, who helpfully provided an intuitive, bovine-based explanation. In supervised learning, each time we see an image of a cow as input, we are providing the corresponding cow label, but it is implausible to collect all labels required for such a task. Unsupervised learning takes in the same cow image and seeks to learn a powerful representation of it without labels. In the self-supervised approach proposed here, labels are derived from co-occurring inputs across modalities, providing redundant signal. Learning then proceeds by minimizing the disagreement between class labels predicted from each modality, rather than matching predictions against an external annotation set. This is an idea that underlies a number of modern approaches. It's also worth noting that in the modern literature, the distinction between self-supervised and unsupervised learning, as given here, can become a little blurry. A general way to think about the redundancy found in multimodal signals is that the redundancy comes from the context surrounding a piece of information. In the natural language processing community, unlabeled text corpora have been used for a long time to provide low-level supervision for neural networks, with the hope that the distributed representations learned by these models will enable them to generalize. One example of such models are autoregressive models, in which the joint probability of a sequence is factored into a product of conditional distributions, with each element in the sequence conditioned on the previous elements. Then, a network can be trained to maximize the likelihood of a text corpus under this factorization. For example, a network can be trained to predict the next character in text to enable compression, or to predict the next word to learn a language model. A slightly more adventurous use of context was explored by the word-to-vec skipgram model, which was trained to predict the collection of words surrounding any given word in the corpus. This is simple to train without labels. You simply pick a word in a sentence, mask its neighbours, and then try to predict those neighbours from the current word. This work was really a breakthrough in terms of language modelling performance, and highlighted the critical importance of having lots of training data in getting good word vectors. More recently, various multitask masking schemes have been considered. Perhaps the best known is BERT, which was trained to predict randomly masked words in a sequence, in addition to predicting the next sentence in a corpus. This work showed, amongst other things, the benefits of using a high-capacity transformer for language modelling. It's perhaps a little less obvious how the same approach can be applied to computer vision. The strategy that has been developed has been to train a neural network by tasking it with playing a game, which is often referred to as a pretext task. Now, typically, we don't care about the performance of the model on the pretext task itself, but we hope that by solving it, a model learns good representations of the visual world. Work by Carl Dursch and colleagues illustrates this idea nicely. A network is shown two image patches. These image patches have been cropped from nearby regions in the same image. The pretext task for the model is to guess the relative position of the red dashed crop to the blue crop. Here's an example. Ask yourself, where does the red dashed crop belong to relative to the blue crop? Here's a second example. Again, where does the red dashed crop belong to relative to the blue crop? When you worked out that the answer to question 1 was probably bottom right and question 2 was probably top middle, you made use of your knowledge of buses and trains, despite almost certainly having never seen this particular bus or this particular train before. The key idea is that a model can only solve these questions once it learns about cats, buses, and trains, and importantly, no labelling is required to construct this task. This seems like a cute idea, and it is, but a warning is needed. Sometimes, the model won't solve the task in the way that you wanted. In this work, Dursch et al. Found that the network can learn to cheat by exploiting a low-level signal, the chromatic aberration that results from a camera lens focusing different light wavelengths differently. One colour, typically green, is shrunk towards the image centre relative to the others. Once the network has figured this out, it can solve the problem trivially by determining the absolute locations of the patches relative to the lens without learning anything at all about cats, buses, trains, or the host of other interesting objects we'd like it to know about. The authors solved this problem by randomly dropping colour channels from each patch so that the network could not rely on this cue. But still, it provides a cautionary tale. Constructing pretext tasks requires a great deal of care. Partly because it works so well, and partly because it's a fun research problem, researchers have come up with a number of creative pretext tasks for training deep neural networks. Some examples include training a network to inpaint by removing patches of images and requiring the model to fill them in, requiring the network to solve jigsaw puzzles by giving it a shuffled set of patches and asking it to rearrange them to match an image, colorization, in which a model is given an image whose color has been removed and then tasked with predicting the original color version. There is training a model to count. This is a slightly ingenious idea. The network is given image patches and has to count objects in those patches in such a way that when applied to the full image, the total object counts match the sum of the object counts across each patch. Other work has trained a model to invert a GAN by training a second GAN to generate the latent codes of the original GAN. One particularly appealing pretext task is to train a model to group pixels according to optical flow. The idea here is to train a model that learns pixel embeddings that are similar if and only if those pixels tend to move with the same velocity in videos, which is a way of encoding the prior knowledge that the pixels on a common object tend to move together. Clustering has also proven to be highly effective. Here, a network alternates between clustering its own feature space and classifying the cluster membership of each image. Finally, rotation prediction can be used to exploit human photographer bias. We tend to photograph things the right way up, so we can rotate images and ask the model to predict the rotation that has been applied. This is also surprisingly powerful. I'd like to talk in a little more detail about a task formulation that has emerged as one of the most powerful mechanisms for self-supervised learning, namely instance discrimination. One motivation for considering this idea stems from the observation that, despite training with semantic labels, fully supervised convolutional neural networks also appear to capture visual similarity between instances. Given an input image of a leopard, the classification scores of a fully supervised model are strongest for the class of leopard, but also for highly visually similar classes like jaguar and cheetah, and much less so for classes like lifeboat, shop cart, and bookcase. An interesting question is then whether the same property would emerge if we trained a model to discriminate between individual instances rather than semantic classes. One work from Wu et al. Explored this idea. It trained a CNN to map all image instances of a dataset to 128 dimensional vectors, storing them in a data structure called a memory bank. The model was trained to encourage each instance to be mapped to a different location on a 128-dimensional unit sphere, such that each image, when encoded with the CNN, would uniquely retrieve its memory bank vector. This model can be trained without labels, but empirically nevertheless learns strong image representations. Momentum contrast considered an extension to this approach. The motivation behind this work was that instance discrimination works well, but memory banks have an issue. On the one hand, recomputing the features stored in the bank, i.e. one feature per image in the dataset, for every update to the CNN parameters would be prohibitively expensive. On the other, if memory bank instances are not regularly updated, they grow increasingly stale with every optimization step, which is suboptimal for instance discrimination. MoCo, or momentum contrast, aims to avoid this staleness issue by first replacing the memory bank with a queue of recently encoded samples, fewer than the full dataset, and encoding queue samples with a momentum encoder, which is formed from a slow-moving average of query encoder weights. MoCo uses some additional terminology. Keys refer to instances encoded in the queue with the momentum encoder. Queries are instances to be compared against keys. Positive pairs are queries and keys originating from the same image, and by extension, negative pairs are queries and keys originating from different images. The instance discrimination task is then to match up queries against the keys that represent their positive pairs using what's known as an info-NC loss, which is essentially a standard cross-entropy softmax. Finally, the resulting query encoder then provides a useful representation for downstream tasks. The methods we've discussed so far have focused principally on learning general image representations. However, the ideas behind self-supervised learning have also been applied to tackling more specialized downstream tasks. One lovely piece of work by Vondrick and collaborators showed how to learn a tracking model by performing colorization. The key idea is to use colors across unlabeled videos as a source of supervision. The model is given a black and white frame that it needs to colorize, and a reference black and white frame. At each location in the input frame, it is tasked with pointing to the location in the reference frame that contains the same color as the current location. This color is copied across to the input frame from the color version of the reference frame so that a loss can be applied at the same place in the true colors of the current frame. In practice, this can be implemented by training a CNN that produces a low-dimensional embedding at each location of an image, then performing pointing from the target frame to the reference frame by simply comparing the similarities of the embeddings at each location in each frame. Given enough data, the model indeed learns to solve this task, and the authors show that without any labels, it gains the ability to track objects across frames. Another direction has considered learning object key points without supervision. The idea, shown here for cat faces, was to learn a model that would learn to detect consistent locations on an object without any labels. The approach here was to use a concept called viewpoint factorization. The essence of this idea is if you had a good key point detector, it should fire on the same point of the cat's face even as the cat's face moves around. In practice, that can be encouraged by enforcing what's known as equivariance. As the image is translated, the key point is also translated by the same amount. Since we have no annotations, just images of cat faces, these translations, and other geometric transformations, are generated via synthetic image warps, and a loss is used to ensure that the key points move consistently with the warps. Another direction has sought to learn powerful video representations with a simple idea. A model takes in several video clips, one of which has had its frames shuffled. Training a model to predict which clip was shuffled learns representations that are particularly useful for action recognition. We now turn to pseudo-labelling. I'd like to talk briefly about semi-supervised learning and the pseudo-labelling algorithm. Semi-supervised learning considers a setting in which a learner assumes access to both labelled and unlabelled data during training. Typically, to provide benefit, the unlabelled data is assumed to be significantly larger than the labelled data. Pseudo-labelling, which is sometimes also referred to as self-training or self-labelling, is a term that refers to some variation of the following algorithm. First, a classifier is trained on the labelled data. Next, the classifier is used to predict the labels of the unlabelled data. These labels are referred to as pseudo-labels. The classifier is then retrained on the pseudo-labels. Often, this process is iterated by regenerating a new set of pseudo-labels, retraining, generating new pseudo-labels, etc. A nice illustration of this algorithm is provided by the work of Yarowsky, who focused on the task of word sense disambiguation across a full corpus. Here, the task is to determine the sense in which a word is meant. For example, the word plant may refer to a manufacturing plant or a live plant. The algorithm proceeds by obtaining an initial small collection of labelled samples and then using them to train a classifier. Then, it predicts labels for unlabelled sequences, keeping those that have high confidence and optionally filtering and expanding the labelled sets via some NLP heuristics. This stage is then repeated until convergence to a final state. The reason for mentioning this algorithm is twofold. One, it's a pleasingly simple algorithm. Two, when large quantities of data are available, it works remarkably well in a wide range of settings. David Yarowsky, author of this work, noted that it thrives on unannotated monolingual corpora. The more, the merrier. As an example application in computer vision, pseudo-labeling was applied to improving large-scale image classification performance by taking ImageNet as a source of labeled images and JFT 300 million as a source of unlabeled images. The method, referred to as noisy student, trained an initial model on the labeled data, inferred pseudo-labels, and then retrained a higher capacity model on the pseudo-labeled data, making heavy use of data augmentation before repeating. Noisy student led to significant gains over ImageNet-only training, highlighting the effectiveness of this technique. More broadly, I think that pseudo-labeling algorithms are likely to prove increasingly valuable in future, as manual annotation simply cannot keep up with the scale of sensory datasets that are now being created. We've reached the end. Thank you for your attention.